Bhattacharya presently is the Sunanda and Santimay Basu Chair Professor of Astrophysics, also head of the Department of Physics at the Ashoka University. Prior to this, Dipankar Bhattacharya has been a member of faculty in the Inter-University Center for Astronomy and Astrophysics and London Research. Professor Bhattacharya obtained his master's in physics from the Jellyfish University, his PhD from the ISC Bangalore. He carried out his postdoctoral research at the University of Amsterdam and University of California, Santa Barbara. He is a fellow of the Indian Academy of Sciences and National Academy of of Sciences. He is also a member of Judicial Steering Committee of the Commission B of the International Astronomical Union. Basically, his research focused in high energy astrophysics, including compact star, cosmic exploration. He has been associated with the Indian Space Astronomy Mission AstroSat for over 2 decades. He is currently the chair of the Science Working Group. This is about what about the this introduction, but more than what I know last from my student time, I know Professor Dipankar Bhattacharya is the very famous astronomy, not only theory, he has a parallel exposure in the observation astronomy on from the beginning. His also famous work, as I know, is the GRD science. It's a very active role in the GRD science from the Indian community, and lots of models developed by him in that.
Thank you so much. And it's a generous introduction, and it's a pleasure to be here. And thanks to the National Space Science Exhibition for making this possible and asking me to give me my talk. So I was asked by the organizers to talk about AstroSat. Since I have been associated with AstroSat as for a long time, I'm also chairing that science working group. So clearly, it's my privilege and pleasure to be able to talk about what AstroSat has been doing and delving also into a little bit of history about it. So let me begin my talk about exploring the universe with AstroSat. AstroSat, obviously, means astronomy satellite, and this is the first Indian observatory class astronomy satellite. If you go to ISRO and look at its documents, this is called AstroSat 1. Although we just call it AstroSat. So it's an Indian. Okay, so now, why is this not changing? Changed here.
Maybe battery problem.
No.
That
This happens. While sharing, it happens. It only shows first page. Some other settings.
Something needs to be done for sharing.
Sharing itself.
So can
Share
the LAN
it
port is
again.
working? Can I give a LAN connection?
I'm not sure this laptop will.
This is not because of land.
I think the network is fine.
Maybe you can reshare it again.
Share different happens in Google Meet.
Okay, so share a window then?
Select your entire screen. Entire screen.
Yeah, so entire screen is what I have done. Let's see that. changed
Yeah.
here.
Yeah.
No, it's
Changing now.
Did it?
Yeah.
Okay.
Yeah. Yeah.
All right. That's, okay. So this was the first time that we in the scientific community in India adopted the data satellite, and it was a big, big journey. It was a very long one, and you can see it started the conceptualization in 1996. The observatory was launched in 2015. So it's a journey of 2 decades. But this journey of 2 decades is not a wasted journey. Extremely eventful and educated journey, which allowed this mission to be built in a large multi-institutional collaboration. There was no such multi-institutional collaboration that India was involved in astronomy before. So this created a culture, and that has helped not just AstroSat but in astronomy across the board in India. And all of us were learning about space as well. Many technical details which had to flow from historical institutions and that. Especially took time. So now I have changed the slide. Either it's very slow or it's very slow. I don't think it's changing.
No, it's not working.
can work with the LAN connection will be better.
Land.
I will see if the LAN port is working. This one, the LAN port was not working. If you have a dongle,
Now it is
now it is
okay, so this has to do with
connection.
to do with just
The Wi-Fi is slow.
what is extremely slow. This is not a practical way of doing it.
So maybe you should change the slide and then speak on this one.
Okay, so what I was going to say is why do you want to do space astronomy at all? Why do space? And this is just a quick example. In the year 1572, Tycho Brahe recorded an explosion, a supernova explosion, and that is recorded in his journals. And if you go to that same location in the sky today, take your good optical telescope, take a look, and this is what you see. Do you see the remnant of the explosion? I can't see very much.
The 8-1. 8-1.
No,
Not.
no, it's at the center.
Oh.
Okay. Now, if you look at it in X-rays, they're exactly the same size picture in X-rays. This is what it is. And there is, of course, a major amount of gas moving very fast, extremely hot, which is present in there. But you're not seeing anything in optics. And that is because there is a lot of dust in the industrial medium between us and this object, which just completely obliterates the optical light. But in X-rays, this is just a beautiful picture. And but the point is that we cannot observe the X-rays from the ground.
Yes.
Please come in.
Just we have started.
Oh.
So we have started.
Yeah, we went round
we
and
have-
round.
Down and down.
It's a little slow also because the slides is changing through Google Meet is getting fast. That we'll see. I really don't think this board is on. activate the land into orbits. Virtually, not detecting. That's something partly because this is not over there.
It is changing.
It is changing. It is changing so far.
Okay, okay. Then,
So let's.
keeping it like
Maybe because there was a conflict earlier.
That might have been a possibility.
Make it bigger and see. Yeah. Just bigger.
Yeah.
हाँ ठीक है
That is
What is land card?
Land card is earlier Wi-Fi is little.
I think there was a conflict.
this is not a one. Yeah. So you can't see X-rays from the ground. If you want to see that picture, you have to go outside that. And this is the diagram of atmospheric capacity as a function of wavelength. And when the opacity is low, that's the part that you can observe from ground. As you can see, there are only a few small windows. You have the optical window. This is our multicolor spectrum that you can see with our eyes. Then infrared window, but you need to go a little bit higher than that. Radio window is good, but a very large fraction of the electromagnetic spectrum is not visible from the ground. And this is why space astronomy has become very important. Because we know now that objects emit over a large range of electromagnetic bands. And if you restrict ourselves to the optical band, we will be missing out practically almost a large fraction of the phenomena that occur in it. So that's the reason, primary reason for sending something to space. And that was the primary reason to send AstroSat into space as well. And the AstroSat wavelength coverage is indicated here. So it's just a little bit of the visible and then all shorter wavelengths. So near ultraviolet, far ultraviolet, soft X-rays, middle X-rays, hard X-rays. Going all the way up to touching gamma. Today, the highest energy that the AstroSat can observe is 500 kilometers, half a million electrons. This, to compare the bandwidth, let's say our eyes are sensitive to this, actually just about a factor of 2 from the red end of the spectrum to blue end of the spectrum. AstroSat goes from 2 electron volts to 500 kilo electron volts. That is factor of 25,000. So that's a major change in bandwidth that you can simultaneously observe from one platform, and there are very few observatories in the world which have this capability. Actually not. So this was one of the niche areas which was already designed into AstroSat in the first concept. Now, what do we see as we go to different wavelengths? But why do we really need to make all this effort to observe something from space going to other wavelengths? What other new information can I get? I already showed you the example of the supernova. Now here is just a galaxy, Garden Variety Galaxy. This is Andromeda Galaxy, which is our neighboring big spiral galaxy. And you take a good optical telescope, take a picture, you see. You can see there is a lot of light, a lot of diffuse light as well as point light. You see gas, you see stars. If you take the same object and take a picture in ultraviolet, you can see that you still see this shape, but not all of this light. The sources of light have become fragmented, pointed, and very concentrated in certain regions. And those are the regions which are harboring hot stars. And hot stars are newly born. So hot massive stars are very well outlined when you go to ultraviolet. When you go to optical, you really don't see this so prominently because so much other light, both from older stars as well as bright gas emission, obliterates the bright point light emissions from regions of Mars. So the ultraviolet image, as I said, captures very hot stars, they are massive, short-lived, newly born, and study of galaxies in ultraviolet band therefore reveals the process of formation. And if you remember how the X-ray image looks like, it's completely different from the rest of the ultraviolet or optical. And that's because the sources that are being seen here are not at all the same sources which you are seeing in optical. So these are sources where gas is getting extremely hot, million degree Kelvin. And how do you get a gas to million degree Kelvin? You have to either have a very energetic collision, like I showed in the supernova, shock wave moving at very heavy, or the gas has to fall into some deep potential well, and the release of gravitational potential energy will heat it up to very high temps. So largely most of these point-like objects are of the latter class. There is a deep potential well, gas is falling into getting hot and emitting X-rays. And these deep potential wells are provided by typically complexes, which are remnants of stellar death. So we saw at one end when we observe in ultraviolet, we're looking at phenomenon of stellar birth. When you look at X-rays, we're looking at the end product of stellar. Remnants in both diffuse remnants.
Why are there so few spheres?
The
big sphere, there is so few.
only this here.
Yes.
No, this is a field of view of Sunanda. Each of these is a field of view.
Okay.
So these are individual images which are just stacked.
Not like the other one.
No, no, it's multiple fields of view which have been just arranged together. And there's some gap in cover, so that's why they look like individuals. There is no spheres in there. So both the diffuse remnant, which is remnant of stellar death, the supernova remnant I just showed you, as well as compact objects, which is white dwarf, neutrons like that. They provide deep potential wells, which is also produced in the X-ray. So you have at one end the birth, other end the death of stars. The stars are born from condensing clouds of diffuse gas in galaxies. And in gravitational collapse, the gas heats up and ignites nuclear fusion. And as the nuclear fission starts, the heat generated by nuclear fusion provides balance against this gravitational. And that's how we have stars. Most stars we see are in that. But nuclear fusion means that you're converting one element into another. Start from hydrogen to convert to then we will convert helium to carbon. But at some point, this is going to run out. The process of fusion cannot continue forever. So once the fuel has run out, this heat generation will stop, and again, the object will collapse. And this time, it will collapse catastrophically. Or suddenly, leaving compact remnant. So the compact remnant could be a white dwarf, where the rest of the star is going to be expelled relatively slowly, but it will still be expelled at some significant speed. They create planetary nebulae. These are probably the most spectacular optical objects in the sky. Most of the pretty images you see from Hubble or James Webb Space Telescope and so on, they're all objects of the sky. They make really pretty. Then supernova explosion, an example of this we showed you, and a subclass of supernova explosions also produce gamma bursts. I'll come to that. The compact remnants that I mentioned. So what type of compact remnant will be produced depends on the amount of gravitational squeeze that you are applying to matter, and how much gravitational squeeze you apply depends on the mass. If the mass is less than about 1 1.4 times the mass of the sun. This limit is known as the condition limit. Then the object stays as a white dwarf, where it's basically sun-like mass squeezed into Earth-like size. And stabilizing pressure. Now we have no thermal pressure because no nuclear burning is happening. The stabilizing pressure here comes from the degeneracy of electrons, which means you have squeezed the electrons so hard that all momentum states are occupied, electrons being Fermi particles and Pauli exclusion applies. So the momentum states are all occupied. You have some high momentum. And those high momentum electrons provide pressure. And that pressure is sufficient to hold the star in this gravitational collapse as though the mass. If it happens to be more than that, then this cannot continue to collapse further into a smaller object. And if mass remains less than 2.5 times the mass of the sun, roughly, then it can find another stable point with stabilizing pressure coming from the degeneracy pressure of neutrons now, plus repulsive strong forces between nuclear material. Those together can provide support to masses up to about this much, where the size becomes roughly about 10. Now you can see that these also descend from the nuclear burning star masses of something about 10 solar mass or less, this between 10 to 40 solar mass, and if the mass happens to be more than this of the compact object, then there is no support. The collapse will proceed all the way to produce a singularity. You get a black hole which will be surrounded by a horizon. And these require, if they are being formed from single stars, masses roughly about 40 solar masses. So now that you have this compact object, you can see that you have taken the sun and squeezed it into very small size. So therefore the surface gravity is. So once gas falls onto the surface of it, because of the enormous speed it acquires falling into this gravitational potential well, when it either strikes the surface of the object or the gas particles collide with each other, they get heated to very high temperatures and they emit X-rays. And this, in the deep potential wells, all of these white dwarf neutron stars and black holes have deep enough potential wells to generate. Where does the gas come from, which will fall into the potential well? Most often, a binary companion of the object, where the donor star matter gets pulled from the surface of the donor star and then spirals in and eventually it lands up at the bottom. So this is called an accretion disk, and this process is called accretion process. And such objects are called accreting binaries. An extra binary system will have a compact object at the center, a donor star, mass going from donor star to the top. Now, one particular characteristic of these objects is that these sources are highly variable in intensity. And they have winds, they have jets, they have flares, and the study of this variability of emission is rich in information about the object itself as well as the flow that is happening around. So, the study of the variation of information all the time. And the timing process proves accretion flow very close to a compact object. And this allows the measurement of mass, spin rate, magnetic field of the compact object itself. Now imagine you have a compact object in neutron stars, which is 10 kilometers in size, located very far away, many thousands of light years. There is no telescope either on Earth or in space you can use to resolve the size of it. But imagine an orbit of a piece of gas which is going around this star. The closer it comes to the star, the faster it will move. And the intensity associated with the pure parcel of gas, if you see it, it will keep going up and down, because sometimes it's coming towards you, sometimes it's going away from you, sometimes it's leaving behind the object, sometimes it's not. So that rate will tell you at what rate it is orbiting this contact. So just by looking at the time variation, you can then deduce what is the size of the orbit. And the size of the orbit is related to the size of the star. There is no way you can, by a resolution of a telescope, find the 10-kilometer orbital size. But through the timing, which will be in the millisecond per microsecond, you can find this very easily. So timing is an extremely important tool to characterize all kinds of phenomena near contact. Once you put a limit on the radius and you know the mass, it can actually help find the properties of matter at high density because that decides the mass radius relation. It can also provide tests of general relativity because the gravity there is so strong, all processes manifestly require general relativity to be described. Newtonian reality is adequate. And you also see that the intensity variation pattern depends on the wave. And that spectral change in the intensity variation also helps reveal the nature of mass flow, what is coming from the jet, what is coming from flare, what is coming from the incoming matter flow. All of that can be derived by looking at the spectral dependence of intensity variations. So now the key strength of AstroSat is that it makes possible most detailed study of intensity. And it does so across a large range. As I said, 2 electron volts to 102 electron volts. And detailed imaging of nearby galaxies at ultraviolet, which also enables that. So AstroSat ultraviolet telescope is among the most highest resolution with a large enough field to contain full galaxies. The AstroSat design allows recording of individual photon strikes in all the detectors, starting from ultraviolet all the way to RSS. And these are most versatile observations. You can record the photon strikes, you can bring them anywhere you like. You can bring them in detector space, you get an image. You bring them in time space, you get intensity variation. You bring them in energy space, you get spectrum. So in one set of recordings, you have encoded imaging, timing, and spectroscopy, all of it. So it's most versatile observing mode. And AstroSat has the ability to find polarization points. At energy is 100 and above, 100 kiloelectron volt and above. It's possible to measure polarization with AstroSat. So all this combined, it makes it an excellent tool to study newly born stars and remnant systems. So those are the two areas where AstroSat has major strengths. So it consists of multiple instruments on the satellite deck, 3 units of large area X-ray proportional counter, which operates in mid-X rays. At the center there is a twin telescope, which operates in ultraviolet. We've got 3 bands, far ultraviolet, near ultraviolet, and visible. Then there is a soft X-ray telescope, which is a focusing imaging telescope, which is at the edge. And there is one more detector which goes to the hardest energies, highest energies. That is a cadmium nickel measure. So these are the 4-pointed instruments, and then there is another instrument which is mounted on the side and rotates on its axis. This also consists of proportional counters with some foreign mass imaging device on top. So it keeps track of what is getting brighter, what is getting dimmer in this half of the sky which it looks out to. And as that points to different directions, it covers the entire sky. And it lets us know which source, for example, has gone right now. And it's good to observe. So now it's been 7 years since AstroSat. Over time, aging occurs of all these things. So currently, not all the instruments I am showing here are fully operational. The near Orbit channel on EBIT is not no longer operational. Of the 3 axis unit, 1 unit is working perfectly, another unit is slightly degraded, another unit is switched on. The same thing is true for Scanix 512. But all of these instruments did take scientifically useful data while there. And in all of these instruments, there is still sufficient sensitivity available for it to continue operating and take useful data. So this is a picture in the assembly room before it was sent for integration with the rocket. This is the rocket, and this was launched on 28 September 2015. Just to give you an idea, the integrated satellite weighed about 1.5 tons, and the rocket weighed 320. Putting on top of that. It was launched in 650-kilometer altitude, circular 6 degree inclination orbit. It's got an orbital period of 98 minutes. So, if you take an orbital trace on Earth, it will cover this yellow region which I indicated. And the ground station is in Bangalore. It's just slightly north of the orbital track. And when it comes up above the horizon, to the time that it goes down below the horizon, the Earth station tracks it, commands, sends commands to it, then downloads data, and rest of the time it is observing autonomously, and data gets recorded on board in that. It gets downloaded when it has the next pass to the ground station. One of the advantages of this near equatorial orbit is that it avoids some nasty regions called the South Atlantic anomaly, which is the strongest here, and these are gradually decreasing contours. And as you can see, this cannot fully avoid it, but it passes through only the edge of it. So this is a magnetic anomaly on Earth, which allows charged particles from the of space to come down very close to the surface. Just like in 2 poles, here is also another. So the charged particle, energetic charged particle density is very high. So as the satellite passes through, the electronics of most detectors have to be switched off. Otherwise, the charged particle bombardment is going to kill them. So when it is passing through this, many of the detectors are switched off. Switched off as it enters here, and it switches on the power. So this removes some amount of time from the time you can observe, but that's unavoidable. But imagine if the track went like that, then the damage would have been much, much bigger. This is to compare the time resolution in vertical axis and energy coverage of AstroSat with some other known missions. But let's not worry about some other known missions, just to indicate what kind of time resolution we have. In the ultraviolet, we have a millisecond time resolution. This is millisecond, this is microsecond. At soft X-rays, we have a sub-second time resolution, about a quarter of a second. And in the mid to hard X-rays, we have microsecond. That's the net distribution of time resolution property of AstroSat. The operations, it starts by an user making a proposal. I want to observe this for this particular reason. And those proposals then go through a review. Once the review is successful, the time is allocated for it, and it gets scheduled. And this schedule is sent to the control center in Bangalore and Kenya. Commands are uploaded to it. And once the observation is done, data gets stored on board, and as it passes the ground station, data gets downloaded. And this downloaded data relatively raw form of data is then sent to what are called payload operation centers. There are different payload operation centers for different instruments, who then generate the ultimate science product which a scientist can use, and then send it back to ISSDC, which is then sent to the data. And the user can then download the data archive. So the data archive gives data to the user who has proposed the observation for a while, and after a while it is publicly available to you. This is a summary of where all AstroSat is pointed in the sky over in the last 7 years. This is as of today. The total number of pointings have been 2,600 plus, and over 1,500 different targets. Which, so that means obviously many targets have been observed multiple times. And right now, this object is being observed, Ashoka, which is supernova. This is being observed for the 8th time. So the number of users, registered users in the database are over 1,500. Half of them come from India, but the rest are distributed across 42 different countries. So far there have been 300 plus journal publications and 250 plus circulars and notices of transient objects. And this number is rising rapidly because initial days the publication rate was slow, and now people are mature in learning how to use AstroSat data. And the curve is very steep because very different target classes have been observed, but the largest amount of time has been spent on complex stars for obvious reasons, and the other large chunk of time has been spent on galaxies for the other obvious reasons, which I have mentioned. This is for study of star formation, young stars, and complex stars, and part of active galaxies has to do with complex stars. Active galaxies are powered by supermassive black holes at the center, which are cousins of the complex stars that are delays are very long. So it was good for a while. Okay, so very different classes of objects that have been observed from some terrestrial stars. Some interesting observations have come from stars, from flares on stars, flares in both ultraviolet and X-rays, and that tells us something about the stellar activity. Different kinds of flares have been seen. Then spectra of some stars have been taken, classifying some stars which are ambiguous. You take especially ultraviolet, more clarity. And also X-ray spectra from active stars, it's telling you something about the magnetic field.
Yeah, no, it's changed.
It's changed. So this is what I already described. So
I have one question regarding that. So many flares you getting here. It is a continuous observing mode or it's a sudden?
no, these are no star is been observed for a very long time.
Yeah.
But some of the exposures have been maybe a day, 2 days long.
Yes.
So you do have some probability of catching it. Yes. Yeah, so what I was saying was that in some cases these are serendipitous, and in other cases they are somewhat longish observations. And then the example, this is a symbiotic star, the spectra are confirmed by using ultraviolet grating. And then this is a coronally active star, SSP spectra, with soft X-ray spectra, giving us some idea of what is happening in the night. These are some examples. These are not the only ones. There are a whole lot of other observations of this. I'm just showing you some examples, but there is a whole class of observations and publications on these objects. Star clusters is another area where very active work is going on. So you have star clusters come in two types. One is old stars, tightly contained, highly dense clusters called globular clusters, and clusters of newly formed stars which are more loosely bound, and the open stars. And both varieties are being actively pursued in AstroSat telescope. And rare types of UV bright stars are coming out. For example, there are certain stars which, for a globular cluster, are too blue. So given its age, you expect the star to have a certain color. There are certain objects which are too blue. And once you look at the ultraviolet spectra of that object, in many cases what you find is that along with the blue spectrum, there is an UV spectrum of another star, which is actually a companion to it, which in optically could not see. And this is a white dwarf. So this was the binary system, and particularly the white dwarfs that are being seen here are somewhat unusual. They are extremely low mass, less than 0.10 of a second. If a star normally evolves and then leaves a white dwarf in our present universe with no mass exchange with any other star, then you will get white dwarfs of the order of half in 0.67, not below. For 0.1 solar mass star to evolve in a white dwarf, it will take 10 times the percentage of it. It cannot happen within this time. So these objects definitely tell us that there has been a binary history, and what kind of binary history can produce such objects is also being revealed by the book. Then horizontal branch and extreme horizontal stars are also stars which have lost varying amounts of envelope while evolving itself. These are stars with helium core burn, but different amounts of envelope have been lost. As a result, you see stars that with different colors but same number. That's called the horizontal. And through the ultraviolet spectrum, one is able to A, easily find these objects, and B, study their properties. Then come to diffuse gas. I talked about planetary nebulae making predictions. This is one such planetary nebula. If you look at it in optical, this is what you see. Now, if you look very carefully at this picture, why are we taking such a big frame and put this object here? So you can see a faint glow around here. That's the far ultraviolet glow, and this is coming from the ultraviolet light which is being produced by this nebula being used to excite molecular hydrogen. And the fluorescence line of molecular hydrogen is producing this. So, it's the first time discovered fluorescence, and it's now been seen in multiple patterns.
Which wavelength?
Hmm?
Which wavelength it's coming?
This is in far ultraviolet. Now I'll tell you the wavelength. Then, here is a old supernova, very big, and this is one of the fields of ultraviolet. And this, I'm showing you just the kind of detail that ultraviolet telescope can observe at far ultraviolet and near ultraviolet. So this is just a little few wisps of the edge of this shockwave. You can see very clearly demarcated in far ultraviolet, far better than in optical. And since one also has the X-ray telescope with it, you can take a spectrum also. You can take a spectrum of it and find what is the composition of it. And you can see these characteristic lines of different elements and find the composition of what this is. So this is not the usual stellar composition. This is material that has been thrown out and synthesized in the supernova. This as I mentioned, is one of the key focus topics of AstroSat, tracing star formation in galaxies. This is a far ultraviolet image from AstroSat of the Andromeda galaxy, of which other images I showed before. And you can see that emission is concentrated from star forming regions, and there's a full survey carried out of M31 and other nearby galaxies like small magnetic cloud, large magnetic cloud, and a full catalog of all sources that are prepared, with properties of all these different ultraviolet sources. It's an extremely rich set of data, which is useful for everybody. Then another example of a galaxy where again you see bright star forming regions, the beautiful spiral galaxy NGC 2336. And the point is, these are not only galaxies. Galaxies come in so many shapes, sizes, masses, environments, that studying galaxies is like studying a full zoo of. And in fact, there's a citizen science project where galaxy images are put up and people are asked to identify galaxies, classify galaxies. That project is called Galaxy Zoo. So it is really nice. So I have shown you two examples, but this is not all. There are many different types of galaxies which are all being pursued, with AstroSat observations, and very interesting also. Emerging, in particular, for example, galaxies in groups. So in the group environment, there is excess gas, and the motion of galaxies through this gas affects the galaxies themselves. And for example, you see these fronts, galaxies moving this way, and then there's a shock front, and stars are forming there. Here is a galaxy, it's called the Jellyfish galaxy. This galaxy is moving through the group medium this way. The gas is actually pushing gas from the galaxy out. And then you see these trailing regions which are no longer bound to this galaxy, they're forming stars. They're basically forming stars outside of that. So all this is being revealed by ultraviolet. I don't have time to go into all of these images, but there's a lot of rich astrophysics that is coming out from this observations. A couple of things I want to just mention. This is, I told you about gas being stripped from galaxies being affected, gas moving away from galaxies. As I said, we see galaxies in all sorts of shapes, sizes, environments, and also in stages of formation. The blue compact galaxies are galaxies which are being assembled. They have just started growing as galaxies, and mass from around is falling into the galaxy, and the galaxy getting bigger. So samples of such blue compact galaxies have been observed in the distance range of about 1.2 to 2.8 billion years of light travel time away from us. There is a project that has been taken up for AstroSat VIP, and finding something very interesting. If you look at the optical image, it is of a certain size. If you look at the far ultraviolet intensity distribution, it is white. If this is optical, it is far ultraviolet. If there is a tail of far ultraviolet outside the optical core of that. And this means that these are all newly born stars. Some gas is falling in from outside, forming stars already, and eventually these stars will then accumulate into the galaxy, as well as the gas will accumulate. But the light from older stars is so much in the galaxy, in optical, that you don't prominently see this thing. Whereas in far ultraviolet, only young stars are visible, and you can clearly see. This was published a few months ago in Nature. Book by Bob. And this also is a observation which was quite groundbreaking. So this is a galaxy which was found by AstroSat, which after AstroSat found bright ultraviolet emission from it, people went and looked, and they found also in HST images galaxies in the same place. And by combining these observations, one could find that there is a huge amount of Lyman alpha photons which are leaking out of the galaxy. So these are ionizing galaxies. These ionizing galaxies are responsible for the intergalactic medium having been ionized after the initial bursts of galactic motion. So such ionizing galaxies have been observed at very high redshift, very low redshift, that is very large distances and very close to us, but not in any other. And this is all the first example of the observation of the intermediate range. So this sort of closes the gap between the history of star formation in galaxies as a function of time from the birth of the universe to now, how the history of star formation in galaxies have changed can be put together by observation. And that's why it's a very, very important piece of observation. The look back time of these galaxies was 9.2 billion. I also mentioned about active galaxies, where you have central object is a supermassive black hole which activates matter and then produces time varying emission. And all types of observations have been taking place of active galaxies, including X-rays and ultraviolet, both temporal and spectral observations. And there are interesting evidences, for example, a truncated accretion disk, which came out from UVIT observation, found hot gas distribution, star formation, Asian feedback in galaxies, as well as from the fluctuation spectrum, the intensity variation as how fast the intensity is varying. You can take a Fourier transform of it, and you can make power spectrum of it. And from the shape of that power spectrum, from this mean that you observe in the power spectrum, you can estimate the mass of the system. That also is being done from astrophysics. So coming down to compact objects, they said they include hard dwarf neutron star black holes. And one of the earliest compact objects that we observed was the Crab pulsar. It's a fast spinning, strongly magnetized, isolated neutron. It's not accreting matter. But it produces very bright emission all the way from radio to gamma rays. But it's not located very far away from us. So this is Crab pulsar pulse profile observed at multiple wavebands with AstroSat. But one of the most interesting observations that AstroSat could do was to find hard X-ray polarization. So this is the Crab pulsar pulse profile, and you can see this is polarization position angle. It's more or less steady at some value around 140, 145 degrees. So if you plot this, so here is the nebula, the X-ray nebula. This is what the pulsar is. The nebular axis, nebula has a sort of symmetry axis. And that symmetry axis is actually the spin acceleration. And the polarization vectors, if you draw them, they are very closely aligned with this thing. Now, this reveals some striking information about where this high energy emission is coming, X-rays and gamma. If you look at the polarization vector in optical or longer wavelength, they undergo significant change in polarization and position angle through the pulse. That's not happening here in these wavelengths. And the only possibility is because polarization position angle is tied to the magnetic field projection of the magnetic field. The emission comes from photon emission. The polarization is always perpendicular to the projected magnetic. So if the polarization is steady, that means in the emission region, although the pulsar is spinning, the projected magnetic field is steady. This cannot happen within the inner magnetic field, because as the pulsar rotates, the projected magnetic field is being changed. But outer part of the magnetosphere, which is called the wind region, there magnetic fields wind and then make a spiral structure which is parallel with the next one. So the magnetic fields are equatorial plane with respect to the spin axis, and therefore the polarization vector which is perpendicular to the magnetic field is parallel with it. So this almost confirms that these hard X-ray and gamma ray emissions don't come from the inner part of the magnetic field, but from the outer part. And this is the first observation of polarization that we did. Coming to accreting neutron stars, we have two types: high mass companions, low mass companions. One of the things that we have been pursuing with neutron stars with high mass companions which all are accreting X-ray pulsars because they're getting the spin, all this variation in intensity, and then you see pulsars. If you look at the spectrum, then you see these dips. And these dips occur because there is a cyclotron resonance. Cyclotron resonance occurs at an energy which is the 12 kilo electron volt for a magnetic field of 10 to the power 12. And the 10 to the power 12 volts which is the magnetic field. So, in the X-ray band, when we see these dips, which is this, we can estimate the magnetic field. It's a very valuable tool to estimate that. So we have detected this in several objects. The energy range between 5 to 45 kilo electron, 6 kilo electron volts. And then, at least for one object, people have been observing this for a long time and trying to see whether the magnetic field of the neutron star is changing. And our observations have also been put in the basket, and then we have done now a modeling. The spectral line energy depends both on the luminosity of the object and an intrinsic time component. Our idea is to try and find this intrinsic time component. And what we find is that it dropped initially for a bit and then just back. So this tells us that this is not something that is intrinsically happening to the magnetic field of the neutron star. It's some kind of a blanketing that is happening by the matter that is falling outward. And if you look at how the matter comes and settles on the surface of the neutron star, creates a mound, and as the mound grows, the emitting region moves a little further away from the surface of the neutron star, and you get a lower. After a while, the inflow rate and the outflow rate from the mound stabilize. The mound height remains constant. The exposed magnetic field to the external observer remains constant. So this behavior that we see of spectral line is actually reflected in the mound dynamics and the intrinsic magnetic field of the neutron star. Coming to neutron stars, the low mass companions, low mass companions take long time to evolve. And these neutron stars are much older than the other neutron stars. The magnetic fields are much lower. The kind of effects that you see here are not spectral ones, but you see temporal behavior which are low and high frequency quasi-periodic oscillations, and correlated spectral and timing behavior, millisecond oscillations, X-ray bursts. All of these have been studied by a lot of people. Some of the interesting things that one found, for example, was an example of X-ray bursts, which is thermonuclear bursts, which happen on the surface of the neutron star when the matter accumulates and nuclear fusion ignites. So very, very close set of bursts, and this is very rare occurrence. Typically, it has a certain recurrence rate, but now suddenly there are 3 very good. Then one also found that after these bursts, before the burst there is a persistent emission, then there is a burst, and then the burst goes away. But after the burst is gone away, you see that the persistent emission has actually increased now, and it increases through the burst. So the emission from the burst is causing some change in the accretion flow. The accretion flow itself is increasing for a time, and that was a discovery with AstroSat, and now for many of the burst sources. During the burst, there are sometimes you see this burst oscillation, very fixed frequency when you look at the Fourier transform of this, and that is related to the spin frequency. The spin frequency is not otherwise seen in these objects because oscillation is very hard to find. But during the burst, you can find the oscillation. Coming to black holes now, as I said, this is one of the strongest active areas. So this is one slide which I suffered because it had overlays and it converted to PDF. But what we have here are, for example, things like quasi-periodic oscillation. These are power spectra. Sometimes you have broadband noise, sometimes you have quasi-periodic oscillation at high frequencies, sometimes at lower frequencies. And other objects, you can have a broadband noise, and you have noise cutoffs and so on, break frequencies. So all of these have been observed from accreting black holes. I would have liked to show you how this relates to the black hole physics. That panel is actually giving me, but doesn't matter. Believe me that all these spectral changes as well as the temporal behaviors give us valuable information about the accretion program. We go to some examples. This is another such periodic oscillation in power spectrum. This is frequency, intensity, and particular fluctuation frequency. And this frequency happens to be strongly correlated with the slope of the spectrum. So not the power spectrum, but the energy spectrum that comes out of the ground. And this can be understood as the oscillation arising in some kind of a compromising cloud. It's one of the strongest correlations ever discovered between these two parameters. And this is done. Here's an example of another thing that you can discover if you happen to be lucky sometimes. During an observation, the spectral state of a black hole, Cygnus X3, changed dramatically. It was spectrum was like this, and suddenly it became like this. And at the same time, there was a radio flare. So this actually caught a jet in the process of being ejected. Some of the key parameters that we want to discover about black holes are the masses and the speed. And one of the techniques that is being adopted worldwide is to take a very good continuum spectrum, and from the shape of the continuum spectrum we can decipher the temperature distribution of the material in the accretion disk and the inner edge of the accretion disk. Where it cuts off depends on the mass of the spectrum. So by modeling the continuum spectrum, you try to infer where the disk cuts off, and then from that to infer the mass of the spin. And this is one example of a combined observation of AstroSat and Chandra telescope. And from that, the probability distribution of spin parameter is all very close to very high spin. One is the maximum spin in these units that are. But there is also another way to try to estimate, and that is, for example, in this object, max is 18.070, where, like in the previous case, I showed you this, different periodic oscillation spectrum peaks. So once you have multiple peaks in the power spectrum, and you take a look at the relation, in some cases you find this beautiful relation. But the frequencies are strongly correlated. And this can be modeled into what is called a relativistic precision model. So what you have is some special area in the disk, probably the inner edge, or some other area where the intensity is maximum. But since there is a massive black hole at the center, the orbits here are not like a plane. They have precessions. There are three different kinds of precession. One frequency is the orbital frequency itself. The other frequency is if the orbit is in a plane and it's like elliptical, the orbit precesses. You may have heard of the precession of the helium or Mercury. That. And then the orbit is slightly inclined in the node of it. So these three frequencies have three different magnitudes, and they follow a certain relation. And these three lines are the predicted relations between these. And you can see the observed frequencies follow those relations. And once we do find something like this, this is directly related to the mass and spin of the black hole. And you can then put in the required equations and then try to infer the mass and spin of the black hole. And this is what we find for this object: mass around 10.5 solar mass and spin parameter around 0.75. But you can see the precision of the spin parameter, 0.725 to 0.8. The highly precise measurement of the spin of the black hole. Once you're lucky and the black hole shows you these figures, not in all cases. Continuing on black holes, now is the birth of black holes. Gamma bursts are supposed to signal the birth of black holes. There are two possible pathways to fill a problem. One is a massive star, more than 47 mass or so. At the end of the stellar evolution, you produce a core which is more than the neutron star mass limit. It collapses and directly into the black hole. And a little bit of the material stays behind. It gets accreted into the black hole in the process it launches a jet. And if your line of sight happens to be along this jet, you see a very bright for that. So that's the possible source of gamma burst. A similar thing can happen not from a massive star to begin with, but let's say two neutron stars which come together and merge due to gravitational radiation, and then form an object too massive for a neutron star mass limit. It forms a black hole, and the rest of the process is same. So only difference happens to be in the duration of the burst. Here you have more material, the burst lasts longer. Here the material is less, burst lasts much less time. So people have classified them as long and short. So the emission mechanism of this gamma, fine, you are launching the jet, but how are gamma emitted? So there are not so very clear diagnostic techniques. There are many possible ways of doing it. You can have a photospheric emission, you can have synchrotron emission, you can have Compton emission, and there are models which will give you full fit to the spectra from any of these here. So how can we discriminate? One possible discriminator is flow. And this is where AstroSat has the ability to possibly put that to use. AstroSat is a fairly prolific gamma burst detector. 520 odd gamma bursts detected today. And of the very brightest ones of these, AstroSat is able to measure. So in first 5 years of gamma burst sample, we found 20 such objects for which this measurement could be attempted. And in 5 such cases, we actually detected finite polarization. In other cases, we detected upper limits. So this is clearly a very important addition to the gamma burst science. And there was one satellite which is dedicated to gamma burst polarization, which was launched in 2017. That is the Chinese satellite Polar. Unfortunately, it operated only for a few months and then it malfunctioned. The follow-up of that is going to come, and they're also going to continue this. But if you look at time-resolved emission, time-resolved polarization, then you can find something even more interesting. For example, this gamma burst, it had 2 episodes. The first episode has a spectrum which has a large black body tag component. And the second episode has only a power law component, which is typical of synchrotron. If you measure polarization, this section of the burst is very poorly polarized. There is no detected polarization. There is strong detected polarization here. Exactly as you expect. If this happens to be from synchrotron emission, there is a large thermal component. So it's not as though that we are looking at all these emission mechanisms in exclusion to each other. Obviously, all of these things actually happen. Different parts of the burst may be powered by different types of emission. And that's the realization that is coming to us now as we go through the gamma burst polarization data. There is another one, it's very interesting. You saw a change in spectrum. This is hardness ratio, which is a measure of the spectrum. This is from the Fermi satellite. So this part of the burst had certain hardness ratio, then it suddenly changed, and then it changed back. If you look at polarization, this part had a certain polarization angle. Angle changed by 90 degrees here, and then came back. And this means that there is a combination of toroidal and poloidal magnetic fields in the jet, and your view axis is slightly wavered. So there's slight precession in the jet. So sometimes you're seeing this part sometimes. So all of these inferences you can draw from polarization. It's very productive. Last thing I want to mention is a Nature Astronomy paper which has appeared on 30th of November. again has to do with black holes. And this is time the star is not dying by itself, but it has been forced to die. It's passed close to a black hole and it's been stripped. It's called a tidal disruption event. And the key thing to look at is these panels, where there's a lot of temporal variation in this. And this fluctuations in 1,000-second time scale or so tells us that the relativistic species. So earlier people thought relativistic jets emerged only from active galactic nuclei and gamma. But we now see that even when a star gets stripped as it is passing close to a black hole, at least in some cases, it can produce very little. So that's all I have. So just to conclude, AstroSat has completed 7 years in orbit. It's performing well, and the large number of targets have been observed. Much of the data is freely available for anyone to use. We have science support cell at Ashoka, which can assist people with data usage as well as making proposals for new observations. And new observing proposals are being sought annually. Next call will be around January, hopefully Girish will tell. So the target of opportunity observations can be proposed at any time. And these observations continue to make important advances in the area of star gas, formation galaxies, star formation galaxies, nature of compact objects, gamma bursts, and so on. But one contribution should never be underestimated. That it opened a path for community-led astronomy missions in ISRO, and in fact, community-led astronomy missions for anything in India. And following this, several subsequent missions are being planned, people are active, people are discussing, and hopefully there is a bright future to come. Thank you very much.
Question from audience?
Oh, you can. Someone is asking.
No. I just give opportunity
I would
to the
also like to
students.
introduce
Yes.
Dr. Sita,
Yeah,
who is
yes,
actually the principal investigator of AstroSat. She is in the audience.
And also Simon.
Yeah.
Also
I will begin to show questions.
Chandra and Mission.
So do you think infrared is something really important that is in this? I know it could not go in with.
Yeah, so in infrared, it could not go because it's got technical
Yeah,
challenge,
that's
right?
true.
Because the cryogenic
But
is
as a scientifically as the wavelength region that's not sampled here. Do you think that's something that should
not compared to JWS.
no.
Yeah.
Yeah.
Then we will not have the article.
So would any like a
Now,
small mission?
when we do a mission, we should do a niche mission because space missions are expensive. And we can do something, let us say, different, but it has to be something different from what JWS is.
No, as in the context of AstroSat, like because AstroSat is still in orbit, would any small instrument that is specifically for infrared, which will simultaneously observe with AstroSat, add to the value in the investigation that we do?
Transformation
Very
areas
physically
are
there.
certainly. But there are simultaneous observations are useful when you're studying variables. Right? So there are areas in transformation side that there are highly variable. They are infrared with that. So you use infrared from a space-based platform to use ALMA and use something like AstroSat near where you can't do anything. But so that is a good combination.
Then another comment. In case of IR, you need cooling.
Yeah,
That is
yeah.
a big challenge.
right.
For
So as a cryogenic source.
cryogenic is important.
Yeah, so I understand in this
That's,
platform, I just
yes.
meant in the same time scale,
Yes,
like
that's a
like-
payload. Another is
Yeah.
huge. Please.
Yeah. So most of the results, You have shown those are on either compact objects or galaxies. I didn't see much of star formation or in this area. Is it because observations were limited
No,
to
so when I say
outer,
galaxies, they are actually really study of star forming region. That is what it means.
not
Yeah,
in Milky Way because of that
No, no.
limitation of 30 degree?
Oh, yeah, around the Milky Way in our galaxy. No, we don't study. UV will not point to it. There are some states. It's too bright.
And I have one more. Uh, you have shown in Cassiopeia A, right? That was being observed 8 times
Yes,
or
yes,
something
yes.
like that. The supernova remnant. Why is it observing repeated?
No, this is it's a calibrate.
So that's a
For
caliber.
the X-ray telescope.
Okay.
So again, I will repeat another question. Uh, that flare, in case of asteroid, very interesting flare light curve generated. One student, he working here, can you tell something? Yeah, we are actually working on the magnetic flare on the stars. So it will be interesting to put a proposal for the AstroSat because we are regularly observing through the ECT 3.6 meter for the spectral identification of the correlation with the magnetic field. That's
Right.
our study. So another flare activity, some of the sources, it will be very interesting. UV flare.
Yeah. So if you are working on pairs, you probably know this Newport effect.
Yeah. Yes.
Newport effect is very clearly seen in
Yes.
Newport.
Yes. Yeah, that would be very much interesting. So my query is that suppose in case of you told that you have to carefully put the proposal where there is chance of flaring within 2 days. Yeah, that calculate right. Yes. For that you have to select the
You have to
source.
select the
and
source, you have to select the duration of
the
observation.
duration.
So the chances are high.
Thank
Yeah,
you.
certainly.
Optimal center is only observed.
There are three of them.
Yeah.
I think 80 microscope here, Proxima Centauri, and the other stars which are this long flares.
Idilio.
80 Leo is not there.
Idilio, we are working on the Idilio. Oh,
Idilio, I don't.
Idilio in
Yeah.
equatorial plane.
Equipeg is
Equipeg,
there.
yes.
Equipeg is there.
Yeah.
So there's one more of that kind.
Recently, PRL has actually analyzed the equipment data and they are seeing a lot of space within that timeline. It's going to come very soon.
They only analyze the first one also.
Yeah, there's
Karma.
come on.
And he analyzed FR country.
If I remember with the X-ray.
So we have now case observation
Even
and case. So case. Case has a lot of data on the flare.
Yes.
So we are
Yes.
using that
Test
data,
data?
case
Oh,
data.
okay, great.
That's right. So we are based on a mainly case data.
Yeah, so what you can do is actually, if you can get some idea of how often it recurs, you can put up a
Calculate
proposal
that, yes.
for SXT
Yeah.
and if possible UV, but mostly SXT.
Yeah.
So you'll get soft Excel.
Or if it's like long duration flares, like 2.
So those
Yeah,
simultaneous
that's,
UV or X-ray flares in 80 microscope here, which looks of the Russian group. It's it will be they obviously will equal.
So
Is that?
oh, yes.
Due to neutron star collides, is it always, I mean, is there a chance that black hole formation won't happen?
Yeah, it is possible. It depends on what is the total mass that remains finally in the merged object. And we still don't know the complete pathways of how much matter will be lost. So it is possible that sometimes that will not form, or black hole may not form for some time. If you get a very highly spinning object, then because of the rotation, it can have a higher mass limit than the Maxwell mass limit. And once it spins down, you get rid of the rotational energy, a late black hole formation.
So when the black hole doesn't form, it again stays in a neutron star form.
Individual stars.
Merging.
Mergers.
Merging.
Okay, let's end speaker from the and also but Sita is here. We are really
Yes.
very glad to be here in the
I'm very
park.
happy to see
Yeah.
this institute. Yeah.
Yes.